Today, we're diving into a mathematical rule that seems really simple, but it leads to a world where, get this, solid objects can be duplicated out of thin air, and some lines have no length at all. It all kicks off with one of the most controversial ideas in the entire history of math.
So, how is this even possible? I mean, really? Well, it's not a magic trick. It's a famous mathematical puzzle called the Banach-Tarski paradox. And while it seems to completely defy the laws of physics, here's the kicker. Mathematically, it's 100% sound. And it's all built on one powerful, deeply controversial idea.
This whole wild ride starts with a question that sounds almost silly. How do you pick a single number out of an infinite set? And I don't mean just thinking of one, in your head. I mean creating a formal mathematical rule to do it. Sounds simple, right? But as we're about to find out, when infinity gets involved, even the simplest choices become mind-bendingly complex. All right, so to really get why this is such a headache, we need to look at the difference between two kinds of numbers that we all use every day.
Okay, check this out, because this slide really gets to the heart of the problem. If I ask you for the smallest positive integer, you'd say 1. Easy. Done. There's a clear rule, just pick the very first one. But what about the smallest positive real number? You might say 0.1, but then I'd say nope, 0.01 is smaller. Then you could say 0.001, and we could do this all day. You can always stick another 0 in there. There's just no rule to pick the smallest, because one doesn't exist. We've got this infinite ocean of options, but no way to just choose one.
So this is where our hero enters the story. Back in the 1870s, a German mathematician named Georg Cantor decided he was going to be the one to solve this. He took on the epic challenge of putting the real numbers into a definitive order, a quest that would change mathematics forever and nearly cost him everything. You see, before Cantor came along, pretty much everybody, from Galileo onwards, just assumed all infinities were the same size. For instance, they knew you could pair up every whole number with a unique square number. 1 goes to 1, 2 goes to 4, 3 to 9, and so on forever. Even with all the gaps between the square numbers, this perfect one-to-one matching seemed to prove that the amount of numbers in both sets was the same. The thinking was, infinity is just infinity. End of story. Or so they thought. But Cantor wasn't buying it, and he came up with this absolutely brilliant proof. Just imagine for a second that you could list every single real number between 0 and 1, an infinite list, but you've got them all, okay? Now create a new number by taking the first digit of the first number, the second digit of the second number, and so on, all the way down the diagonal of your list. Now change each of those digits. The brand new number you've just made, can it be anywhere on your original list? No way. It's different from the first number in the first decimal place, different from the second number in the second place. It's different from every single number on your supposedly complete list. And that was his mic drop moment. He proved there must be more real numbers than natural numbers. Infinity, it turns out, doesn't come in just one size. You've got countable infinities, like the integers that you can actually line up, and then you have these vastly, monstrously larger, uncountable infinities, like the real numbers. This idea didn't just rock the mathematical community, it was a full-blown earthquake. The backlash was brutal, and it was personal. The guy leading the charge was Cantor's own former teacher, Leopold Kronecker. He didn't just disagree, he publicly called Cantor a scientific charlatan and a corrupter of the youth. He saw Cantor's work as a disease infecting the purity of mathematics. But Cantor didn't back down. He doubled down. He then claimed that even those giant, uncountable sets could be put into a well order, a definitive sequence. The only problem was he couldn't prove it. The attacks got worse. Kronecker actively blocked his career path, and the pressure led Cantor to suffer a series of nervous breakdowns. The absolute low point came in 1904, when a colleague stood up at a conference and publicly announced to prove that Cantor was wrong, humiliating him in front of his family and everyone he knew. But sitting in that very audience was another mathematician, a guy named Ernst Zermelo. And as he listened to the supposed disproof, he felt something was just off. And that feeling was about to make him the unexpected hero of Cantor's story. Zermelo dug in and realized that Cantor and a lot of other mathematicians had been unconsciously using a tool that wasn't actually in the official rulebook. They were just assuming that you could make an infinite number of choices all at once, even without a specific rule for each and every choice. So,
Zermelo did something brilliant. He took this hidden assumption and dragged it out into the open. He formalized it into a new fundamental rule, the Axiom of Choice. It simply states that if you have a collection of sets, you can always choose exactly one element from each one. It doesn't tell you how you choose or which element you get. It just guarantees that the act of choosing itself is mathematically possible, even across an infinite number of sets all at once. And armed with this new axiom, Zermelo could finally prove Cantor was right all along. He used the axiom to simply choose a real number to be the first, then choose a second from what's left, and so on, an infinite number of times. He proved that a well-ordering must exist, even if we can't ever possibly write it down. Just like that, Cantor was vindicated.
Now, saving Cantor's reputation was a huge win. But adding this powerful new rule to the foundations of math had side effects, consequences nobody saw coming. This new power came at a price, and it opened the door to a much, much weirder mathematical universe.
One of the first paradoxes was the Vitali set. It's a special collection of points you can make using the axiom of choice. And it has a bizarre property. You can't measure its length. Think of it this way. If you try to build a line segment out of infinite copies of this set, you hit a logical wall. If the set's length is 0, the whole line has to be 0. That's wrong. If its length is anything more than 0, the line becomes infinitely long. Also wrong. Neither makes any sense. The only way out is to accept something wild. The set is non-measurable. It's a collection of points that simply doesn't have a size.
And this freaky idea of non-measurable sets brings us right back to our duplicating ball. The Banach-Tarski paradox uses the axiom of choice to break a sphere into a few of these special non-measurable pieces. Just like the Vitali set, these pieces are so complex and scattered, they don't have a defined volume. And it's this bizarre ghost-like property that allows them to be rotated and reassembled into two spheres, each one a perfect identical copy of the original. So you can imagine mathematics was in crisis. Is an axiom that allows for infinite duplication really true? For decades, the community was totally split. You had one camp saying the axiom is obviously true, and another camp shouting that it's obviously false. The resolution finally came from two giants, Kurt Gödel and Paul Cohen. And the best way to understand it is with an analogy from geometry. For centuries, there was a huge debate over a rule called the parallel postulate. Eventually, mathematicians realized you could either accept it and you get standard flat geometry, or you could reject it and create equally valid but totally different spherical or hyperbolic geometries. It's a choice that basically defines the universe you're working in. And that is exactly what Gödel and Cohen proved about the axiom of choice. It's independent of the other rules of math. You can't use the other axioms to prove it's true, and you can't use them to prove it's false. It just stands on its own. You can build a perfectly consistent mathematical universe with it, and you can build another perfectly consistent universe without it. It's a fundamental choice. So if it's just a choice, why do most mathematicians today accept it? Paradoxes and all? Well, because it's just so incredibly useful. It's a powerhouse. It makes countless proofs shorter and more elegant. It's essential for huge areas of modern math. And in many cases, it lets you extend a proof from a finite case to an infinite one with a single simple step. At the end of the day, the math just works better with it. And this leaves us with the real takeaway. The debate was never really about objective, capital T truth. It's more like choosing what kind of mathematical universe you want to explore. The question was never, is the axiom of choice right? The real question is, and always was, is it the right tool for the job you want to do?